Next, we're going to do some statistical analysis with the regression equation that we have developed. And for that, we have to make some assumptions. Here, we're going to assume that the data that we collected, the X and Y data, comes from a situation that is something like this. That is, you have an X value, right? And then you have Y. And the mean of Y falls on a straight line. And that is given by beta sub 0, not B sub 0, beta sub 0 plus beta sub 1 X. Okay, so that is E of Y is the same as mean. So mean of Y falls on a straight line. So if mean of Y falls on a straight line, then for each possible X value that we have, Y comes from a distribution for which the mean is here. Mean is given by beta sub 0 plus you plug in that X, whatever that you get, that's your mean. So that's the mean, but the actual Y value comes from a distribution around that mean, okay, and that distribution follows normal distribution. Okay, so the mean is on a straight line. Okay, if X is 20, then Y will come from a distribution that is centered over there, given by that. If X is 30, then Y will come from a distribution that is centered here. And each of those distributions will be normal. Okay, so there are two assumptions going on here. One is the mean will fall on a straight line, and the distribution of Y itself in each of those cases will be normal distribution. Okay. And there is one more assumption that you can visually verify, and that is each of these normal distributions, they have the same spread. In other words, same variance. Okay. That is called homoscedasticity assumption. The same variance for each of those distributions. And then to round it all up, all of these different distributions are independent. Okay, so those are the four assumptions. So they are listed here. The errors are independent. Well, the reason why this is given in terms of errors is because Y and error would be the same. So we are not talking about error between the actual Y and the Y hat. So this will be the Y hat, or in the population case, it will be Y minus the mean of Y. So if errors are independent, then the Y's will be independent. The errors are normally distributed. The mean of the error is 0 and the constant variance. It's the same as what I just described to you. So if these assumptions are true, then we can set up an F test. Remember the F distribution that we talked about in chapter 2. And then we can test whether this regression is significant or not. Okay. By significance, what we mean is whether this slope is different from 0. If the slope is 0, then you get a straight line that is parallel to X, and X doesn't have anything to do with Y. All of the means are exactly the same, equal to beta sub 0, and X has no influence on Y. Only if this line has a slope that is different from 0, either positive or negative, it doesn't matter. If it is 0, then X is not significant. If it is different from 0, then X is significant. Okay. In other words, beta sub 1 is significant. Okay. So we can test whether beta sub 1 is equal to 0, which means X is not significant, or beta sub 1 not equal to 0, in which case X is significant. Let's head over to Excel now. So these are the assumptions. Stated it back again. So here is the model and the assumptions. Now we're going to assemble the sum of squares that we have calculated previously in what is called an ANOVA table. ANOVA means analysis of variance. So we're going to look at those variances and analyze that for the regression. So here, the sum of squares for regression, residual, and total are these. We already know that, right? Now the degrees of freedom for each of those sums of squares, okay, they are, for regression, it is k, where k stands for the number of x's. So in the case of simple regression, k is 1. Okay. Multiple regression, it will depend upon how many x's we have. The total degrees of freedom is always n minus 1, the sample size minus 1. And so residual degrees of freedom or error degrees of freedom, often this is also referred to as error. Okay, so residual, error are interchangeably used. So that would be the difference between that and that. So n minus k minus 1. So that's our degrees of freedom. So this is sum of squares. Now ms stands for mean square. So mean square is you take sum of squares and divide by the degrees of freedom. And when you do that, you get mean square. Okay, so you get MSR, that is mean square regression, like SSR is sum of squares regression, MSR is mean square regression, and MSE is mean square error, that is SSE divided by the degrees of freedom. So once you have that, then the ratio, remember if you go back to chapter 2, F is a ratio between two sums of squares. So for it to follow a theoretical distribution, we really need to divide a variance by a variance. A variance is sum of square divided by the degrees of freedom. So these two are two different estimates of variance. So F is MSR divided by MSE. So that's your F, and then you can use the F dot dist dot RT function to find the p-value. Significance of F is the p-value. So p-value using F.